Today we
Good
are
afternoon, sir.
going good afternoon. We are going to discuss antenna array. We have already discussed about antenna, upwave dipole antenna, and dipole antenna. So the basic part of antenna is over, and now we will consider antenna array. Now, when we discussed about antenna, we discussed about its characteristics. One of the characteristics of the antenna is radiation pattern. So we had discussed about radiation pattern also. In the radiation pattern, we came to know about the main beam. Main beam is the beam that gives us the direction. The maxima of the main beam gives us the direction in which maximum radiation occurs. So most of the energy is confined within the main beam. So the area covered by the main beam gets maximum energy from the antenna. So the information is transmitted into an area which is covered by the main beam. And then we saw there is something called a null. Null is the angular region in the direction in which direction there is no radiation. So energy does not propagate in that direction, antenna does not radiate in that direction. We cannot receive any information in the direction of null. So if there is a null, the area covered by null will be shadowed. There will be no reception along the area or over the area covered by the null. And these are two important things about the radiation pattern of an antenna that we came to know. Then we also know that each antenna is associated with its own radiation pattern, which means if we get one antenna, if we design an antenna, then that antenna will have a main beam in a particular direction. Depending on the structure of the antenna, it will have a null in a particular direction, depending on the structure of the antenna and orientation of the antenna. We do not have any control over the main beam or the null of a single individual antenna. Now, this is one point. Second point is each antenna can carry a maximum amount of fixed maximum amount of power. So you cannot give 10 watt power to an antenna and it will radiate 10 watt power. That is almost impossible. In most of the cases, antenna cannot carry high amount of power. The power handling capacity of the antenna is limited. Now, once the power handling capacity is limited, as we know, the power that is radiated by antenna will decrease as 1 by r in the far field. So as you keep on increasing the distance, and the amount of power received will be decreased, which means we cannot radiate or we cannot cover a large distance if we use a single antenna. Therefore, we have got three problems now. One is covering a large distance using a single antenna. Second is radiating or orienting the main beam in a direction that is desirable, in the desirable direction. Third is orienting the null in a desirable direction. These three problems are with us. Now, what are the physical situations where we will deal with these problems? The first situation that comes to your mind is suppose we are at our border, the country, we are at the border of the country, and outside the border there is an enemy country. So there are two countries, one and both of them are enemy to each other. then each one will try to jam or to disrupt the communication of the other country, particularly the military communication. So near the border, if country A is the friendly country and country B is the enemy country of the country A, then country B will try to jam the antennas of country A. Now how they will jam this antenna? What they will do is they will send electromagnetic signal in the direction of the main beam of our antenna or of the country A's antennas main beam. In that direction they will send signal, which will be high power signal and noisy signal. Therefore, the signal to noise ratio will decrease. Noise will keep on increasing because more noise is coming in the direction of the antenna. So antenna is receiving more noise than the signal. So signal to noise ratio will degrade and it will hamper the communication. To avoid that, country A will orient its main beam in some other direction so that it will be not in the direction of country B, or country A will orient its null in the direction of the country B. So whatever signal is coming from the country B is in the direction of the null, so that will not be received. And so this is a particular situation where we require the orientation of null and the main beam to be as per our requirement. Similarly, look at the cell phone towers. So when you have a cell phone tower or mobile tower, they will radiate in a direction, or a TV tower, they will radiate in a direction that is desirable to them. So in those directions, the power is to be concentrated in those directions. And they will try to cover maximum area, so the power should travel to a large distance. So in those cases, if I use a single antenna, that will not be sufficient. So to avoid that, what we do is we go for an antenna array. If we go for an antenna array, the antenna array consists of more than one element. So instead of having one antenna element, we will have more than one antenna element. So more antenna element, each element will radiate some amount of power. In the far field, as you know, the electric field is a vector quantity. So field from on the antennas, each antenna element will be vectorially added in the far field. So there will be more power. There can be more power if they are vectorially added in phase. Then there will be more power. And in fact, we will see that depending on the phase, the orientation of the main beam will also be controlled. So using more than one antenna, we can control the orientation of the main beam, orientation of the null, and we can add power. So this is what is the function of array. So we are going to discuss, that is why we are going to discuss antenna array. These are the importance of antenna array. We are going to discuss the antenna array. In the process, what we will do is we will do an analysis of simple linear arrays. What is linear array, that we will define later. In the analysis, we will consider these terms: array factor, pattern multiplication, and array directivity. These are the three terms that we are going to discuss in our discussion today. Now here you can see there are dipole antennas, about 7 dipole antennas are there. They are separated by a distance d. Each element is separated from its adjacent element by an amount of d. And these antennas, the center of these antennas, they are along a straight line. So when the center of the antennas, or center of mass, that we can say, or centroid of the antenna lies along a straight line, then we call this antenna to be a linear array. This antenna array is called a linear array. This is an array because we have more than one antenna. When we have more than one antenna, then we call it to be an array. And these antennas have their center of axis along a straight line. This straight line is called the array axis, and since the center of each antenna is on this straight line, a straight line is a linear line, or it is a linear curve, therefore these antennas are called linear antennas. Now on the two sides you can see two radiation patterns. On the left side you can see the maxima is perpendicular to the antenna axis. On the right side you can see that the maxima is along the array axis. When the maxima is along the array axis, we call this to be an end fire array. When the maxima is perpendicular to the array axis, we call this to be a broadside array. Any other, so all arrays will be either end fire or broadside, or in between these two, either between broadside and end fire. So that is what we are going to discuss, the broadside array, the end fire array, etc. So and now, before going into this, let us try to refresh our memory. Before going into the details of the antenna, let us try to refresh our memory. So for many antenna, most of the antennas, they radiate electromagnetic field which is not directed. They can be in any arbitrary direction. If they are in any arbitrary direction, then there is a problem in point-to-point communication. Point-to-point communication is called POP communication. So problems will be in POP communication because they are not directed. You are radiating from one point, it is not received at the desired point, or the other point is the desired point. So radiation does not go to desired point. When radiation goes to desired point, from one point to the other point, both the points are desired, then it is called a point-to-point communication. Otherwise, it is not a point-to-point communication. Now, POP communication or point-to-point communication requires greater directivity in the desired direction. This is not possible. Getting high directivity is not possible with a single dipole antenna or using a isotropic source. These are not possible. Single dipole antenna is a more it gives you a figure of 8 pattern as well as it is omnidirectional. So point-to-point communication is not possible there. Then we know the vector, if you consider vector, because electric fields, we are considering electric field, we can resolve a vector into vectors of different directions. That is possible. That is a vector property of the vector. Any vector can be resolved into many other vectors. So each vector has its own direction. So that can be resolved into different directions. Electromagnetic field is a vector quantity that we know. Since electromagnetic field is a vector quantity, so simultaneous radiation from a group of antenna is the array antenna. That can give electromagnetic field in a desired direction. So desired direction corresponds to one vector, and the radiation by each antenna gives into the resolved vectors. So that gives you one antenna. This group of antenna is called array antenna. Generally, the radiating system with several antennas, group of antenna means several antennas, they are spaced properly to get greater far field strength from an antenna array. So if you get more strength in the far field, it will radiate to a larger distance. Now we will come to linear antenna array. What is a linear antenna array? The elements, antenna elements in the array there are more than one element, so the elements are along a straight line. A uniform linear antenna array, this means these elements are equispaced. So spacing between two adjacent elements is same and they are along a straight line. Then the phase, electrical phase between two adjacent elements is constant. So if you take, suppose you take three elements. So electrical phase between 1 and 2 is same as 2, 1, 3. So that phase remains constant. Or if you take four elements, between 1 and 2, suppose it is alpha, 2 and 3 it will be 2 alpha, 3 and 4 it will be 4 alpha. So they will be in uniform phase progression. So either progression is 0, which means everything is alpha, or it is uniform, which means alpha, 2 alpha, 3 alpha, 4 alpha, in that manner. Either of these two is called uniform phase progression.
Sir?
Now let us come. Hello. Yes. You want to say
Hello?
something? Yes. Tell me. Hello.
Sir, POP
Point to point. POP stands for point to point. So if you have 2 points, you want communication between 2 points, point A, point B. But if the communication is only between 2 points A and B, then it is a POP communication. But if the communication is between point A, point B, point C, then it is not a POP communication. POP is point to point communication. Okay? Okay. So now let us come to the basic part. The basic antenna that we discussed is an isotropic source. The isotropic source or isotropic antenna is a hypothetical antenna. It does not exist physically, but we assume that there is a point source, and the point source, if you have a point source, it will radiate equally in all directions. So the isotropic antenna is called isotropic element or isotropic radiator also. This we will use as the reference antenna in the array analysis. Then we will use the pattern multiplication that you will know. So to include any actual physical antenna. This radiates equally or uniformly in all directions, which means if you are at the center of a sphere of radius r, all power radiates uniformly through the surface, which is 4 pi r square of the surface of the sphere. PR, which is the power radiated in radial direction, is equal to amplitude of S being the Poynting vector or magnitude of the Poynting vector, that is the total power radiated by the isotropic source. Okay. And PR is equal to average power density or P average. Total radiated power that we find using the PR. So that is total radiated power is P rad, that is integration of S being the Poynting vector is the power density. So power density is power per unit area, therefore integration of S over ds. So that is P rad. So that you can write this way, integration of S over ds, that is since above. Amplitude of S is equal to PR, so take PR outside the integration. It is independent upon ds. PR is a constant with respect to ds. So take PR outside the integration. So PR integration over ds. When you integrate over ds, that gives you 4 pi r square. This is for isotropic source. It gives us 4 pi r square because of the sphere. Sphere surface area is 4 pi r square. So it is P average, PR is equal to P average. So P average into 4 pi R square, that gives us P average is equal to P rad by 4 pi R square. This we have already discussed earlier. Our radiation intensity U, that we defined as R square P rad, R square P average, that will be, we know what is P rad from using radiation intensity. P rad is equal to integration of radiation intensity with sine theta over d phi d theta, that we write as integration u d omega being the elemental solid angle, omega is the solid angle. Now directivity of isotropic source is equal to 1, that we know. So because solid angle d omega, when we integrate it, that gives us 4 pi for a isotropic source. P rad is equal to 4 pi u0. U0 is isotropic source radiation intensity. These are the things that we have discussed earlier. Now there are other sources. Beyond isotropic sources, there are other sources like hemisphere, sine square. These sources actually give us the radiation pattern which is hemispherical. Then we call it a source with a hemisphere. If the radiation pattern is sine, then we call it a source with sine. If the radiation pattern is sine square, then we call it a source with sine square. So let us see. P rad is equal to integration u d omega. That let us integrate d omega is from integration from 0 to 2 pi and 0 to pi by 2 over d theta d phi, and d sine theta will be there because of d omega. Then um, that is called to 2 pi um. Directivity is radiation intensity of the source by radiation intensity of the isotropic source. So that you can write as 2 pi um is equal to 4 pi u0 being the radiation intensity of the source, isotropic source. So from that you can say d is equal to um by u0 is equal to 2. This is for a hemispherical antenna. Then for a sine antenna you can write the same thing. Um now becomes into sine theta. So already there is one sine theta. Now you have into sine theta. So that gives you sine square theta. If you integrate that integration gives you pi square so once you know what is pi square is to be equated to 4 pi u0. From that you can find out d is equal to by u0, which is 4 by pi, that is 1.27. This is for sine. Similarly for sine square you can find out d is equal to 1.5. Here into sine q theta d phi, that you are going to integrate. Okay. The first is for hemisphere. A pattern is shown here. Okay, next. A hemispherical pattern means half of the sphere. That is what is hemisphere. Then sine u, a pattern is u is equal to sine theta. It is like a figure of 8, inverted figure of 8. Sine square is is equal to sine square theta. So it is again figure of 8, slightly inflated figure of 8. So these are the radiation patterns for which we find out the P rad and the directivity. Now let us come to the array. The array we will consider start with only 2 elements, because as we discussed, array is more than one element. So more than one element, simplest thing is 2 elements. So let us first consider only 2 elements. The array of 2 point sources or 2 isotropic sources, because the basic source is the isotropic source. We will consider 2 isotropic sources. So this is the simplest array. Most simple array is the 2-point array, 2-source array, 2 isotropic elements. Separation between the elements is delta, and both elements have same polarization. So either linear polarized or circular, left circularly polarized or right circularly polarized. but same polarization. Polarization does not change. They have same polarization. So this is the condition first. Two elements separated by delta, by an amount delta, and have same polarization. Then we will consider the superposition of fields. Superposition of fields is obtained by vector addition. So this is determined from the phase of the field from each element. The basic configurations, let us consider the basic configurations. They will have, both the elements will have same amplitude and same phase. That is one consideration. Then they will have equal amplitude and opposite phase. Amplitude means the current that is exciting. So value of the current excitation current, that is the amplitude. Value of the excitation current or excitation voltage. The voltage that you feed to the antenna or current that we feed to the antenna, that gives us the amplitude. So equal voltage or equal current and equal phase current, current on both the antennas are equal, has same phase. So that is equal amplitude and equal phase. Second is equal amplitude and opposite phase, which means phase is 180 degree. There is a phase difference of 180 degree. Equal amplitude and opposite phase. Then third is any amplitude and any phase. So that is the most common part. The third part is most common part. So this is what we are going to discuss about antennas, antenna array, two element array. So we will take a break here. When we come back, we will start with two element array analysis.